Okay, I think it's time. So, any question from this time? So, okay, quick review. This time we go over how to do inverse Fourier transform. No, sorry, inverse Laplace transform. Yeah. So we get this mathematical derivation that we say Laplace transform is just Fourier transform. Where is it? It's just a Fourier transform on this x times e to the minus sigma t, and we can do inverse Fourier transform on this. And it turns out it is some contour integral inside your RC, but unfortunately we don't know how to do contour integral. So we settle for something easier. We say that if we are rational functions, then you can just do partial fraction expansion. We have to do this quite a few times. And you do partial fraction expansion, then you get a whole bunch of terms that looks like 1 over x plus a. And you can just inverse Laplace transform this by already know that by already knowing its inverse, because we have done the Laplace transform two different functions that both get 1 over x plus a, and it will depend on RC. So it's a little less trivial than just write the direct inverse. That is, you need to look for RC. So as we said, RC for Laplace transform is very important. So when you have rational functions, you have a whole bunch of poles, and the RC is between two of the poles, and depends on different RC, then for each pole you will get one of those partial fraction terms, and you need to look for whether the RC is to the right of the pole or to the left of the pole, and you will know whether you are going to inverse into this u of t decaying exponential or this u of minus t decaying exponential. So that's how we do inverse Laplace transform, and today we are going to a different topic that is not too much calculation. It is mainly qualitative things. So we are trying to see how the pole zero plot can help us learn some property of Fourier transforms. But obviously you can do similar thing. As you will see, you can do similar thing to Laplace transform too. But let's focus on Fourier transform first. Focus on Fourier transform here, because most of the time you still like Fourier transform. Yeah. Okay. And so what we'll do, we'll talk about pole zero plot, and for simplicity, we restrict us to rational functions, because if you are not rational, then you can have really weird poles and weird zeros. But yeah, but for now we restrict out to rational functions, and obviously for rational functions you can write it into this product of poles and product of zeros. Okay. So the denominator terms are the roots here are the poles, and the roots for the numerators are the zeros, as we know. And there might be some constant. That's not too important here. Okay, and we are going to show that you can get a geometric interpretation of this whole product by considering each term in polar form. So this is really like each term is a complex number, and you can think about each complex number as a vector and also as a polar form e to the I theta, e to the I theta, and you can read what's the r here and what's the theta from the picture. So here is a very quick example. So maybe the simplest function possible. So what if our original function just have 1, 0, so some 0 at a, so your function is s minus a, okay? And so this s minus a term is a complex value, and we want to see what's it, and as we say, we want to write it as r e to the I theta. So the question is, what is r here and what is the theta here? And so this is like a review for complex number that you learn from maybe calculus class. But anyway, so we also know that the complex number can have a vector interpretation, and it works like this way. So let's say you want to calculate s at s1. Right, so this is x of s1, and so then that value should be s1 minus a. And how you look for s1 minus a in this picture is first you draw s1, and there's a on this complex plane, and s1 minus a will just be this vector from a to s1. See here, from a to s1. And you can justify this by doing the vector addition. So s1 has as a vector is a vector from 0 to s1, and a as a vector is a vector from 0 to a. So negative a is a from to 0. So if you want s1 plus negative a, so it's like this vector plus this vector. So it's you add those two vectors together, then it's just a vector from a to s1. Okay. So yeah, this is the most important thing here in this class. That is, if you have a complex number that is s1 s minus a, then when you draw it on picture on this complex plane, then that's a vector from a to s. Okay, so the a to s is correspond to this complex vector s minus a. And okay, so now we have this vector picture, then we can just read the r and the theta from this picture. So the r will just be the magnitude, the length of this vector. So the r is just this distance from a to s1, or s1 plus 2a is the same. So r is this length, and what's theta? So theta for the complex number is the angle between this vector and to the real axis. So theta is this angle here. Okay, so you see that any s minus a, you can very easily see what's the r and the theta. Okay, so that's s minus a, and this is when a is 0. We can also think about what if a is a pole. Okay, so if a is a pole, then that means our this Laplace transform is 1 over s plus a, s minus a, and so you just have 1 over this complex value. Okay, and then geometrically it's a little hard to see 1 over vector, but you can think about the complex calculation, right? So maybe let's jump here. So you have 1 over complex number that is written as r e to the I theta. Then from calculation, you just know that's a complex number with magnitude 1 over r, and theta being negative theta, right? Because you just do a calculation. So you see that if a is a pole here, then the corresponding complex number will have a length that's 1 over this length, and the theta is negative over this theta. Okay, any question? I think those interpretations are the only important part, not only part, I guess the most fundamental part of this course. Then if you know this, then okay, so that's just one term, and if you have many terms, then just multiplying together. So you have a whole bunch of complex numbers, they are all in polar form. So you have r1 e to I theta 1, r2 e to I theta 2, etc. and you multiply them together, then you see that the magnitude all multiplying together, so you get the total magnitude is R1, R2, and even more than R3, R4, etc. And the angle will all add together. Okay. So yeah, that's really all the thing we do in this section. We're just going to see this thing apply to different systems. So once again, you have a whole bunch of poles and a whole bunch of zeros. You can mark them on your picture, and then you look at whatever is there. Then you just see what's the angle and the distance of S to all your poles and zeros, and you multiply the lengths together, or multiply the lengths together and divide by the length to the poles, and then the angle you sum together or subtract to the poles. Okay. Sum the angle to the zero and subtract all the angle to the poles. Okay. So that's really what we mean by geometric interpretation. It's just write all the complex number in polar form and think about them in kind of geometric way. So this R in the polar form will just be the distance from your S to your poles or zeros. And if you are poles, then you need to divide your length, and if you are zeros, then you multiply the length, etc. Okay? Any question? Yeah, so any rational function, then you can factor into these zeros and poles and get a feeling of how your big X of S should behave when you move S around. Right? So let's first see an example. So this is a very easy example, kind of like the one we start with. So it's 1 over S plus 1 over 2. So you have the single pole at this S equal to minus 1 over 2. Okay. And now we consider the Fourier transform, because we say we want to consider Fourier transform. So we restrict our S to purely imaginary j omega, and we have this thing. But and then in a picture, what will it look like? So as we said, we will have this pole at minus 1 over 2, and we look at S equal to j omega. So now we think about when we move j omega around, what happened to our vector this 1 over j omega plus 1 over 2. And as we say, we can think about it geometrically. Okay, so we can think about it geometrically. So it will be 1 over this vector from your minus 1 over 2 to omega. So and then you can write down the angles and the length from the geometry here. So for example, the length of this, you can just do the triangle equation. So it's 1 over 2 squared plus omega squared. And because it's a pole, so it's 1 over the length. So length you need to take 1 over. So the length square, yeah, so the magnitude square of your Fourier transform will just be 1 over omega squared plus 1 over 2 squared. And the angle, so the angle here, then you can once again do trigonometry. So you know this is omega, this is 1 over 2. So you know this angle is arctangent to omega divided by 1 over 2. So that's arctangent to omega. And as we said, once again, because we are dividing these numbers, so angle you should take a negative sign. So you get these two things. And okay, so you can read from the geometry to know how this function should behave. Yeah. And but you can also kind of just read it from this thing. But I mean, you can also derive all these things from doing calculation. From you just know this x of j omega. But as a usefulness here is you can use your geometric interpretation to know some property of these things very quickly, right? Because for example, you look at this picture, and you see that so you know that when omega equals to 0, then it's closest to this pole. So you know that when omega, and so this length will be shortest here, and when you do like dividing 1 over, then you know the magnitude should be highest when your omega is 0. And you know that when you drag your omega to plus infinity or minus infinity, the length gets longer and longer. And yeah, so the length goes to infinity, and so your big X should go to 0 as your omega go to plus infinity or negative infinity. And you can also do some interpretation of the angle here, so you know that omega equal to 0 here, then the angle should be 0. And omega goes to plus infinity, then it should become pi over 2. And so it's actually negative pi over 2. And if you go to negative infinity omega, then it should go to, the angle should go to negative pi over 2 and the extra negative sign, so that's plus pi over 2. Okay? So that's what we like to do on this pole zero plot. Any question? If not, then let's see the next example. Okay, so now we're going into a little tricky place because we skipped 3 chapters. Okay, so this is something that the book discussed in chapter 6. Anyway, we have seen this kind of equation. So this is called first order system, and it's a system that characterized by this differential equation. And you can see it's first order because it is a first order derivative. And there are some reasons, so you can reasons that you get normalization such that the only constant, like the changing constant here is tau here. Okay? And it's called time constant. But anyway, first order system is a system that's described by this differential equation, tau dy dt plus y of t equal to x of t. And well, we didn't do chapter 6, but you can solve this by what we learned in chapter 4, right? So this is like what we do in the midterm. So you guys should be all very good at this. So you can write big H very easy. Although we do big H of j omega, but big H of s is similar. So big H of s is just 1 over, so s times tau, then plus 1 here. Okay? And if big H of j omega, then it's just j omega tau plus 1 here. And from this, you can solve for small h. And yeah, and later part of the course, later part of the chapter, you will see that how to determine the ROC here. But anyway, I think if we assume initial rates, then the ROC should be on the more stable side here. And anyway, the small h, or you can just do the Fourier transform h of j omega and do the inverse from h of j omega. And anyway, you can solve for small h with this, and the ROC is on the bigger than the pole side. And this is really similar to this previous example here. And so if we draw a picture, you can see that well, the pole here obviously is minus 1 over tau. So it has a pole at minus 1 over tau, and just like before. And so we think about how omega change here, and your x of h of j omega basically just depends on its relation to this minus 1 over tau pole. Okay? And so here are some pictures that was done in chapter 6. And there is a log plot for reasons, but anyway, you see, so it's a log plot, so it's a bit different, but anyway, you see that it has a decaying omega as you expect. So as omega go from 0 to infinity, then so this is the log of the magnitude of h, it will decrease. And it kind of start decreasing at this 1 over tau point. And it makes sense because its length is 1 over tau, so you start seeing the decaying starting when your omega is also about 1 over tau. Okay? And similarly for the angle, as we said, the angle, if you go to infinity, it should become minus 1 over 2. And it has starting to change with around 1 over tau. Right? And so the thing we can learn about the system from here is, well, the important thing So the only parameter here is tau, and it reflects in the fact that the position of the pole is minus 1 over tau. So you can see that if you change this tau, then you will change 1 over tau, and your system response will be a similar form, but will change a different 1 over tau. So say tau larger, then your 1 over tau is closer, then the decaying, the transition will all happen faster, etc. Okay. Question for the first order system. Well, super fast. Maybe we can talk about some property today. Okay, so there is first order system, then there is second order system. It's more complicated. So obviously, the second order system is also described by a differential equation. So it's this differential equation. And well, we now don't keep the constant on here for reasons once again. But anyway, we found out that it's nice to characterize all the constant here in this one. So we have dy dt square, and the constant on dy dt, we write it as 2 eta omega n, and we write there is omega n squared y of t, and it was also sin x of t is multiplied by omega n squared. So I think it makes sense because it's second order, then we have two constants, omega and eta. And it is in this form because then later things are in a nicer form. And anyway, we have a differential equation like this, and it's easy to write your big H of j omega. You can just read it from here, so the numerator should be just this omega n squared. Then the denominator will be j omega squared times this 2 eta omega n times j omega, and plus omega n squared. And then you can do inverse Fourier transform. But now the numbers don't factor into nice integers like we do in midterm, but you can factor it into roots nonetheless. So if you do solve this second order equation here, then you see the roots are the C1, C2 equal to this minus eta omega n plus omega n square root eta square minus 1. Or, okay, sorry, it's easier to say this. So it's minus eta omega n plus minus omega n square root eta square minus 1. It should be middle school math to solve this equation. And then if you want to write down small h, then there is h of this n factor. Let's keep that. And anyway, this is the second order equation. So if you do Fourier transform, then big H is this. And similarly, if you think about Laplace transform, we just replace all the j omega with s. And so s is also has these two poles, and C1 and C2 we talked about before. Okay, question for now. Okay, and now things are complicated because we want to plot this C1 and C2 on our complex plane, but it depends on your eta. And so now you see why we want to write all the constants in this form, because now eta will control nicely how C1 and C2 look like. Because you see that here we have this weird term square root eta square minus 1, right? And eta can really be any number. I guess eta we don't consider negative, but eta can be any positive number. So in particular, so if eta is less than 1, this is negative, so we get the complex roots. And if eta is bigger than 1, then we got real roots. Okay, so there are really two different conditions. Depends on whether eta is bigger or less than 1. And also if eta equal to 1, then we are at some critical point, and we have our two roots will overlap with each other. But we don't consider it particularly. But anyway, so we'll have some plots. And first we consider the case where eta is bigger than 1. And in this case, the systems are quite stable. And so if eta is bigger than 1, you will have two real roots, and they will look like this. They will always be negative. You can check it out. They will always be negative, and the distance between them is 2 omega and square root eta squared minus 1. Okay, and if eta is very large, then you will see that one. So if eta get larger, then obviously the separation get larger and larger. But they are always negative, and one of them will be very close to this 0. I think that's this one, right? So you're seeing if eta is very large, then the first term is minus eta omega, and eta is very large, so this term is about square root eta squared, so that's also eta, so you get like a eta omega and minus eta omega, and so that's about 0. So but you can get a second order term, etc. Anyway, so we see that as eta get very large, so one of them get close to 0, and one of them get very far away. And okay, so let's back to the first case. Anyway, so when eta is bigger than 1, then both of these roots are real. And then you think about our Fourier transform. We move our omega around this j omega axis, and what will happen? And you think about this is basically same as the first order system. So it's very similar, right? Because you have 2 poles, and so you are dividing by 2 poles like here, and you think about the distance to this j omega, and it's similar to the first order system. So you are just, I should say, it's a product of 2 first order terms, right? And the first order term, they have the same general behavior. So it's like the distance is smallest when your omega is 0, and the distance go to infinity when your omega go to plus infinity or negative infinity. And I guess the angle is different because you are multiplying 2 angles now, but it's also similar. So in the first order system, your angle is like plus pi over 2 to negative pi over 2, and then now you just have 2 angles in integral. So your angle is from plus pi to negative pi. Okay. So this is real simple, and also, as we said, when your eta goes to plus infinity, is very large. One of the poles is very close to the axis, and you think about your thing is 1 over the pole, right? So so when 1 over the pole is really close to the axis, then the magnitude is just going to be dominated by this pole. Right. Yeah, so most of the thing is going to be dominated by this pole because it's just closer, and so the magnitude is going to be dominated by how you react to this pole, and the angle depends on your frequency. So the angle when you are close to this pole, then so when you are low frequency, the angle will also be dominated by this pole, because like when you change here, then this angle changes very quickly, and this angle changes slowly. But say if you are like quite far away from this pole, then the angle to this pole is already fixed to pi over 2, and then you will get the second step. Then when you go to a larger distance, then the angle will depend on, will get the pi over 2 from the other pole later, etc. And let's see, we have a picture. No, we don't quite have a picture in this chapter, but here is something from chapter 6. So here are some second order system that you might build. Is the RLC circuit, or yeah. So this RLC circuit is the second order system. And here we are drawing some picture of the magnitude and the frequency. And here we actually draw everything. So we are drawing even for eta less than 1. Okay. But anyway, so you see that if your eta is eta is small enough, so that this eta is bigger enough, so this Q here is small, then your amplitude your magnitude just decay with your function, because both of those lengths just get larger and larger, so it decay when your omega get larger. Okay, so that's the case for eta bigger than 1, and for eta equal to 1 we have critical value, but so you can imagine that you just have two poles sitting together, but so it's really just a square of a first order system, and don't care about it too much. It looks a lot like a first order system. And the other case is now eta is between 0 and 1. Okay? Eta between 0 and 1, and now things it's more interesting. Now we have two complex poles, so draw it like here. Okay? The poles is so the first let's see, the first term will be the real part, so the real part just is minus eta omega, and then we have a complex value at plus minus omega is square root 1 minus eta square. Okay, this I guess square root eta square minus 1, but now those eta less than 1, so this is imaginary. Okay, we have two roots here. And now we think about what happened when we drag our omega around this axis, and we think about how its distance to this pole up here and this pole down here, right? And you see that obviously when you are closer to one of the pole, then you are more affected by it, because it's one over distance. So because say if you are closer to this pole, then if you are close to this pole, then this distance will get smaller. Then you will get like a spike here. So this length gets smaller, but you are one over the length. So the magnitude will get larger when you are around here, and also you will get a larger magnitude around here. Okay. So here are some pictures. Maybe easier to see this first. So and yeah, so you see, but here are value for different eta. But for now, let's just look at this behavior, right? So this is the magnitude, and we see that when your omega is closer to those two poles, you will get two spike at the amplitude. And also you will get corresponding transition in your angle around these two poles, because you know the angle to this pole is going to change from pi over 2 to minus pi over 2, and then you will get another change of pi over 2 to minus pi over 2. So that's how you see those two change here. Okay. And okay, let's see. And we can see, okay, so the height here is omega square root 1 minus c squared. And we see that the rate of transition is around this c omega n, right? Because the length here is c omega n, so you kind of feel the change when you move around c omega n too, because if you want to get a powerful angle, you need to move c omega n, and that's also when the length here gets changed by a factor of square root 2. Okay, and so here we can see what happens when USC go to close to 0. Okay, so what happens when USC? Oh, sorry, not C. I'm missing. So I should call eta, right? This is eta, this script thing. Yeah. So this eta go to 0, then because the length here is eta omega n, so eta goes to 0. Then the two poles actually get closer to your imaginary axis here, and so we are actually going to see the change around poles be faster. So here are the picture. The picture is actually for different eta. So we fix the omega n to 1, and we are changing different eta. So you see that as eta go to smaller and smaller, the spike here get higher and higher and narrower and narrower. And also you can see that kind of in this angle plot. When your eta gets smaller, the change in angle gets faster and faster. And yeah, okay. So that's the idea. You get 2 poles here, and when you are moving closer to the poles on its imaginary value, then you get a spike around it. And there's also okay. So that's most of the thing. Yeah. Yeah, and as we say, so the closest point for obviously when you want to be closest to this pole, then you should have the same imaginary value. So our value is this omega and square root 1 minus eta squared. Okay, and yeah. But obviously there will be a little difference because you also need to consider distance to the other pole. So the angel spike will be moved a little away from here, but this is a good approximation. But anyway, that's the second order system, and there are more analyses around its property on chapter 2, but on chapter 6, but skip those for now. But one more qualitative thing I want to say is that you can think of this as a non-ideal bandpass filter, because you can just look at this this picture, and you see that the system has spikes around this plus minus omega in place. So you can use this as a bandpass filter. You will pass this band and this band, and and as we see here, how sharp your filter is will depend on what your eta is. Your eta gets smaller, then your filter is sharper. Okay. But obviously there are properties more property you can analyze in the study, but they can all come from this pole zero picture. Okay. Any question? Alright, slower than I expected, so this will be very quick. Anyway, okay, so that's the second order system, and we don't have third order system to analyze. So let's have the last system. Is the opaque system, and well, it's really simple. It's just a name for a system that is. I guess we didn't have the correct definition here, but here is but for idea, here is an example of what is an opaque system. So it's a system where your pole and the zeros have this symmetry. So it's an example where you have a pole at minus a and 0 at plus a. And what happened here is now you think about is Fourier transform on this omega axis. Then the magnitude will have a very nice property that the magnitude of the Fourier transform is always going to be 1, right? Because you think about, you have a symmetry here, you have a triangle of equal distance here, so the distance from your omega to your pole 0 at a, and the distance from your omega to your pole at minus a, those two distances are the same. And now you consider the convex number you want to multiply this distance but divide by distance, so you are just dividing the same thing, and so the magnitude should just always be 1. Okay. I guess assuming your m is 0 and m is also 1, right? Let's go back to our thing. So we are just saying we assume we have a rational function with m equal to 1, and if let's say that m equal to 1, and you have the same 0 and the same pole. You have a 0 here and the pole with negative sign down there, then the magnitude will be 1. Okay, back to opaque system. Yeah. So the idea is very simple. If your pole and the 0 have the symmetry, then then the magnitude will just be a constant. So I guess here we didn't say m equal to 1. So the magnitude will just be the m of your rational function, the big M of your rational function. And the last thing will be a constant is respect to your frequency omega, and that's called the opaque system. Because yeah, if you think about passeband and stopband, then every frequency is a passeband. Okay? And there is really not too much you can say about this, and you can calculate the angle here, right? Yeah, and if you calculate the angle, and now the angle is not going to be 0, so angle you will have a theta 1 here and a theta 2 here. Theta 1 plus theta 2 will be pi, but so theta 1 plus theta 2 is a constant, but remember you are dividing this, so you need to take theta 1 and minus theta 2, and that's not a constant. And you take theta 1 minus theta 2, so there's pi minus 2 theta 2, and that's something. And theta 2, once again, you can take it from arctangent of this omega divided by a. So tangent theta 2 is omega divided by a. Okay. So you can write theta 2 as is arctangent omega divided by a, and your angle is this thing. And anyway, you plot this amplitude, and let's use this easier. Maybe this one. Yeah, maybe use this one. Okay. So the amplitude, as we said, is always magnitude is always going to be 1, and the angle is going from 0 to minus pi, and the minus pi equal to pi to 0. So here is just because how we take arctangent, because tangent pi equal to yeah. Here we see a discontinuity here, but it's just because the angle of pi equal to the angle of negative pi. So you can also think about a picture like this. Okay. This is just how we want to take the discontinuity in arctangent. Okay. Because let's see. So when omega equal to 0, then you have when omega equal to 0, then you have theta 1 equal to pi and theta 2 equal to 0. So at 0 is like pi, but when you have negative, then arctangent, you don't take theta 1 equal to more than pi, and so you get the fake discontinuity here. Okay, any question about opaque system? Okay. I guess you can also think about if you have more of those 0 pole pairs, then but they all are symmetric, then you still have an opaque system. Right. Let's draw somewhere. Let's see, maybe here. Yeah. So let's say if you have like a more poles than 0 here, like this. Let's draw more symmetric. Yeah. So let's say you also have a poles and a 0 like here, then it's still opaque system, because whenever you move around this geometric axis, the angle to the distance to each pole and the distance to each 0, there will be a distance to a pole that cancel out. Yeah. So as long as your point 0 form pairs around your geometric axis, then you will be an opaque system. Okay. And we have 7 more minutes. Let's try to get a little bit more. Okay. So property of Laplace transform. So just like a property of Fourier transform, there are a lot of properties like linearity, time shifting, conjugation, convolution, etc. But the most important thing is not say here. The most important thing here is that so for all those properties, now we need to consider how the ROC combines or changes. Okay, that's something that we didn't have from the Fourier transform. So let's see this example very quickly today. So linearity of the Laplace transform. And linearity was very trivial for all the Fourier transform, but it also looks pretty trivial in Laplace transform, except that you need to consider ROC, as we say. Okay, so linearity, as we say, you have some small x Laplace transform to big X, some small x2 Laplace transform to big X2, then ax1 plus bx2 or Laplace transform to a big x1 and plus b big x2. Okay, so the algebraic part is just as usual, you have a plus b here and a plus b here. But the ROC is weird, okay? So what's the ROC here? You now will have a ROC that containing the intersection of R1, R2, okay? So it's tricky. So there are really two things here happening in these four words. So first is you want the intersection between R1 and R2. Okay? So that's kind of what you want. You want these to be converging and these to be converging. But we also say containing because you can get very lucky and cancel some poles so that your ROC is actually bigger than R1 intersection with R2. So let's see that example here. Okay, so yeah, so this is the example of the cancellation. This is the example where your ROC can extend beyond the R1 intersection with R2. So your x1, actually we just have a big x1 because a small x1 doesn't matter too much. So your big x1 is 1 over x plus 1, and with the ROC being on the right hand side, and x2 is 1 over x1, 1 over x plus 1 plus 1 over x plus 1 times x plus 2, and ROC also on the plus hand side. Okay, and now when we take the difference of those, because on the time domain we take a difference, on the frequency domain we also take a difference just by linearity. Then we see that you can also see these are the partial fraction expansion. This will be 1 over x1, 1 over x plus 1, and subtract by 1 over x plus 2. But anyway, you do this subtraction and you see that the x plus 1 poles cancel each other, so you are left with this 1 over x plus 2 pole. And that means that when you take the ROC, it's going to be bigger than these two, because now you don't have a pole at -1 anymore. So you should extend your ROC to this -2 pole, because as we said, for rational functions, your ROC should end at poles, right? Your ROC should have a boundary on poles. And so yeah, it's really easier to see from this picture. We start with these two functions. So these two Laplace transform. So this 1 over x plus 1 is a pole at -1, and this 1 over x plus 1 times x plus 2 has a pole at -1 and a pole at -2, and the ROC are those things, those two that boundaried by this -1 pole. And when we subtract them, then this -1 pole cancel out. So even though the intersection of the ROC is bigger than -1, because this -1 pole cancel out, so you should extend your ROC to -2. And that's why we say containing R1 intersection with R2 here. Okay. Okay, so I think that's all I want to talk about today. And hopefully we don't get hit by hurricane, by typhoon. But yeah, any more questions? Otherwise, let's see you on Friday. On Friday we should be able to finish this chapter. Hopefully.